Hi, I'm Logan Raj Analilaki Munisami. My metric number is B0422101122.
Hi, my name is Muhammad Fahmi Bejasmi and my matrix number is B0422100064.
My name is Saramidan son of Gurasilat. My metric number is B0422100082.
Now, I'm going to explain about introduction. Computational fluid dynamics CFD is a field of study that utilizes numerical methods and algorithms to analyze and simulate the behavior of fluids such as air or water in interaction with solid surfaces. As a fluid flows over a surface, the velocity of the fluid changes from zero at the surface to the free stream velocity away from the surface. The boundary layer thickness characterize the distance over which these velocity changes occur. I'm going to explain about theory. The boundary layer theory in computational fluid dynamics CFD describes the thin layer of fluid adjacent to a solid surface where viscosity dominates. As fluid flows over the surface, velocity changes from zero at the surface to the free stream velocity away from it, resulting in a smooth gradient. The boundary layer can be laminar or turbulent, impacting the accuracy of CFD simulations. Understanding and modeling the boundary layer are crucial for predicting aerodynamic forces, heat transfer, and other phenomena in various engineering applications, making a fundamental concept in CFD simulations.
Now I'm going to talk about the objective. There are four objectives that can be identified. The first objective is to study the parallel flow over a flat plate using the analysis of fluid. The second objective is to identify the boundary layer that formed by the parallel flow over a flat plate. The third is to find the velocity of the flow over a flat plate using fluid solution. And the fourth objective is to know the effect of different of airflow velocities on boundary layer profile. Now I'm going to present about the geometric detail and dimension. For the construction of the flat plate, there are some geometry details and dimensions that need to be considered and need to be followed. First of all, for this plate, the horizontal measurement, which is H1, that is located below, which is in the direction of the x-axis, is about 0.5 meter. Moreover, for the vertical measurement, which is straight upward to the y-axis direction, and also can be considered as V1, for the flat plate is about 1 meter. In addition, for the line of plot, it is done at the middle of the plate, which the measurement is about half of the 0.5 meter of the horizontal axis line, which is about 0.25 meter.
Right click on geometry, select new design model geometry. Select set plane. Choose sketching, go to setting, and grid, click on show in 2D and snap. Major grid spacing set into 0.1. Minor step per measure set into 10. Go into draw, select rectangle, draw a rectangle. Go to dimension, set the horizontal value into 0.5 and set the vertical value into 1 meter. Zoom the rectangle. Then go to modeling, choose XY plane. Then go to sketch 1. Go to concept, select surface from sketches. Go to sketch, click sketch 1 and apply. Generate. Click mesh. Click the Z plane. Generate and click on the rectangular. Click mesh, insert and face modeling. Click the geometry, click the surface and click apply. Generate mesh. Right click on mesh, go to insert and click sizing. Go to edge, click the top and bottom of the rectangle and click apply. Go to type, select number of division and set it into 50. And click generate mesh. Right click on mesh, go to insert, click sizing, click the left side of the rectangle edge and click apply on geometry. At type, change it into number of division and set to 60. At the type bias type, select the first type of the line. At bias option, select bias factor. The bias factor set it into 70 and generate. Right click on face meshing, go to insert, click sizing and click the right edge of the rectangle and click apply. Change the type into number of division and set it into 60. Select the first bias type and set the bias factor into 70 and select the reverse bias and click apply. Click generate mesh. Click the mesh and go to click the face and click on the surface of the rectangle. Right click on the surface of the rectangle and click airflow. Right click on the left edge of the rectangle and select create name selection and name it as inlet. At the right side, name it as outlet. And click OK. Select the down part, go to create name selection and name it as plate and click OK. Go to the top and go to create name selection and name it as far field pressure. Then click OK. At name selection, you can see all the names. Go save the project. Right click on setup. Choose the double precision and put 2 on solver process. Click OK. Select models. Click whiskers and change into lamina. Click OK. Click materials and click add. Change the density. Change the density into 1. Change the viscosity into 1 exponent negative 4. Click change or grade and close. Select boundary condition. Click inlet. Change the velocity magnitude into 2 and click apply. Close. Click far field pressure and select velocity. Sorry, click symmetry and apply. Click monitors and click residual. Change it into 0.00001. Change the x velocity and y velocity into 0.00001. then click OK. Click Initialization and click Standard Initialization and select Inlet. Change the Y velocity to 0. Click Run Calculation. Set the number of iteration into 1000. Click the number of iteration and change it into 100,000 and click Calculate. So the calculation is complete. Now you can click the State Ratio Towards. Click the ratio tool and change the continuity into 1 exponent negative 0.7. Change the x velocity into 1 exponent negative 0.7. Change the y velocity into 1 exponent negative 0.7 and click OK. And calculate. Click OK. Go to File and Save Project. Previous video we already finished setup and solution. Click Results. Select Z-plane. Click Contour 1 and name it as Contour 1 and click OK. Select the location and click Symmetry 2. The variable select as Pressure and click Apply. And change the number of contours into 50 and click Apply. The variable change it into velocity and click Apply. Click Location and select Line and name it as Line 1 and click OK. The point 1 must be 0.25 and 00. Point 2 must be 0.2510. This is because we chose middle point. Change the samples into 100 and click Apply. Select Chart and name it as Chart 1. Click X-axis and change the variable into velocity U. Click Y-axis and change the variable into Y. And change the location as Line 1. Click Apply. So the chart viewer is done. Repeat the same step for 2.5 velocity.
Repeat the same method for velocity 2 meter per second.
These are the result of XY chart. For the first diagram, it shows the XY chart for the airflow of 2 meter per second. In the XY chart, the x-axis represents the velocity of the fluid flow, which is in meter per second unit in x direction, and the y-axis represents the distance, which is in meter unit from the horizontal plane. The result shows that the velocity increases until 2.1 meter per second, then decreases slightly back to 2.05 meter per second. After that, you can notice that in the chart, the velocity remained constant until reached to the position at 1 meter. For the second diagram, it shows that the XY chart for the airflow of 2.5 meter per second. However, the result obtained is much different from the first one. As you can see in the chart, the velocity increases until 2.65 meter per second, then decreases slightly back to 2.59 meter per second. After that, this velocity also remained constant until reached to the position at 1 meter. From this, we know that as the position moves further from the flat surface within the boundary layer, the velocity will be constantly increases. This shows that there is some approaches of free stream velocity from the flat surface. Finally, the velocity reaches at the condition of free stream velocity at the edge of boundary layer. These are some results for the graph of calculation. As you can see, this is the result of graph of the calculation for the airflow of 2 meter per second. At the horizontal axis, it represents the number of iteration, and for the vertical axis, it represents the number of residuals. In this graph, there are three plots of result, which is for x velocity, y velocity, and continuity. For the y velocity, it increases drastically to 1 exponent to negative 4.5 and then decreases until it achieves to smaller residuals. For the x velocity, it starts from one exponent to negative 0.3 and then decreases more than y velocity until it achieves smaller residual. Lastly, for the continuity, it starts at one exponent 0 and then decreases constantly with x velocity and y velocity until achieve these smaller residuals. For the second diagram, in the result of graph of calculation for the airflow of 2.5 meter per second, in the graph there are also three plots of result which is for x velocity, y velocity and continuity. For the y velocity, it increases drastically to 1 exponent to negative 4 and then decreases until it achieves a smaller residuals. For the x velocity, it starts from the 1 exponent to negative 0.3 and then decreases more than y velocity until it achieves smaller residuals. Lastly, for the continuity, it also starts at 1 exponent to 0, then decreases constantly with x velocity and y velocity until it achieves the smaller residuals. From this, we can say that the calculation obtained for the x velocity and y velocity which flow at the surface is valued different for the different type of airflow, but the continuity achieved will be same.
Okay, hi. Right now I will be present about the result in contour of color coded for the airflow 2 milli per second and 2.5 milli per second. Okay, as we can see, as the air flows over a flat plate, a boundary layer forms near the surface. The boundary layer is a thin layer of air adjacent to the surface where viscous effects are significant. We can see a nice view of boundary layers development. If we can see at the range of velocities, it goes from 0 to little over 2. And despite almost uniform velocity coming in and quickly the boundaries get formed and it grows slowly. Here we can see the thickness boundary layer much smaller than length of plate. Okay, right now the relation of result with the theory. The velocity at the plate is the lowest and it increases till become uniform in the inviscid area, which located above the bounded layer edges. Same goes without project result. The velocity vectors along the plate shows that the velocity of fluid particles at the plate is zero due to the non-slip condition, and this occurs due to the viscous effect where the fluid particles stuck to plate. Effects of different flows velocities at 2 milli per second. Okay, let's go for the velocity profile. The velocity profile with the boundary layer will be exhibit a gradual increase in velocity from 0 at the solid surface to the free stream velocity. The velocity gradient near the surface will be relatively gentle, indicating a slower transition from the stationary to free stream flow. For boundary layer thickness at 2 milli per second, the boundary layer thickness will be thicker compared to the case at 2.5 meters per second. The slower the airflow velocity allows the more gradual build-up of the boundary layer. Next, the effect of different airflows velocities at 2.5 meters per second. Alright, for the velocity profile will show a steep increase in velocity from the surface to the free stream velocity. The velocity gradient near the surface will be more pronounced, indicating a faster transition from the stationary to free stream flow. Alright, at the 2.5 milli per second also, the boundary layer thickness will be thinner compared to the case at 2 milli per second. The higher airflow velocity results in a quicker development of the boundary layer. Okay, why it is happen? Alright, the effects can be explained by the concept of momentum and fluid dynamics. Higher airflow velocities create greater momentum, leading to a more rapid transition from the stationary layer, it is at the surface, to the free stream flow. This result is a thinner boundary layer and a steeper velocity gradient near the surface. The formation of the boundary layer is influenced by the viscous effect. At the lower velocity, viscosity dominates, causing a slower buildup of the boundary layer. At the higher velocities, inertia becomes more significant, leading to quicker establishment of the boundary layer. So, in summary, different airflow velocities affect the boundary layers profile by influencing the velocity gradient and thickness. Higher velocities lead to a thinner boundary layer with a steeper velocity gradient, while the lower velocities result in a thicker boundary layer with a more gradual velocity transition. Alright, I think that's all from us. Thank you.